Something is amiss in our comprehension of the universe. Cosmology is, by all accounts, heading for a standoff on one of its most essential inquiries. How quick is the universe growing? For more than a decade, two sorts of estimations have been in conflict. Perceptions of the current universe commonly find the rate of extension, called the Hubble constant, to be around 9% quicker than forecasts based on early universe data. Analysts trusted that the James Webb Space Telescope, the most progressive telescope ever built, would assist with settling the inquiry once and for all. However, agreement has so far failed to appear. Instead, the Space Observatory has established the inconsistency with incredibly exact groundbreaking observations that threaten to overturn the standard model of cosmology. The new physics expected to adjust or even supplant the 40-year-old hypothesis is now a subject of debate. An intriguing and fascinating possibility is that there's something we do not yet understand about the universe. Join us as we dive deep into how new ultra-deep images from James Webb have just confirmed there is something genuinely amiss with how we interpret the universe. Our universe began with a bang. The Big Bang, energy, mass, and space flashed into reality all within a fleeting moment. Then, the youthful universe was formed. A growing, roaring plasma stock of matter and antimatter particles that jumped into reality, only to obliterate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma ought to have consumed each other completely. However, researchers believe that some unexplored cosmic asymmetry enabled more matter than antimatter to be created, saving the universe from immediate implosion. Gravity compacted the plasma pockets, pressing and warming the matter so that sound waves traveling just over a portion of the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high-energy density of the early universe's packed contents expanded spacetime, pulling a small part of this matter safely from the fry. As the universe swelled like an inflatable, the standard story goes, conventional matter, which interacts with light, hardened around clusters of invisible dark matter to make the first galaxies, connected together by a vast, infinite web. At first, as the universe's substance spread out, its energy density and consequently its growth rate diminished. However, about 5 billion years ago, galaxies began to recede once more at an ever faster rate. The reason was a new, invisible, and mysterious substance known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe expanded, its general matter density dropped, while the dark energy density remained the same, continually making the latter the greatest contributor to its overall expansion. Added together, the energy densities of normal matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, lambda CDM model of cosmology, which maps the evolution of the universe and predicts its end with matter eventually spreading out so far that it encounters an end-time heat death known as the Big Freeze. Many of the model's predictions have been shown to be highly accurate, but here's where the issues begin. Despite much searching, astronomers do not know what dark matter or dark energy are. As Ofer Lahav, a professor of cosmology at University College London, who is involved in global studies of dark energy, said, "Most people agree that the universe's current composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is we don't understand the last two of them yet. An even greater threat to the lambda CDM model has emerged. Depending on what method astrophysicists use, the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Techniques that peer into the early universe show it expanding significantly faster than lambda CDM predicts. Those techniques have been cross-checked and confirmed by countless observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason I can see at this point for them to differ is simply that the model we have between them is maybe missing something. Measuring the universe's expansion takes more than a radar gun. The main technique to measure this expansion looks at the so-called cosmic microwave background, CMB, a remnant of the universe's first light emitted just 380,000 years after the Big Bang. The imprint can be seen across the entire sky and was planned to determine a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this grand baby picture, the universe is uniformly hot and cold, with patches where matter is more or less dense, revealing where baryon acoustic oscillations caused it to clump as the universe exploded outward. This bubble-like structure swelled into the cosmic web, a network of filaments along whose intersections galaxies would be born. By studying these waves with the Planck satellite, cosmologists inferred the amounts of ordinary matter and dark matter, and a value for the cosmological constant or dark energy, slotting these into the standard model to give a Hubble constant of around 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is 1 megaparsec away from us, it means it will recede from us and we from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to increase dramatically from there. If a galaxy is any farther than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second technique to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that expand and contract as they absorb and emit the star's radiation, causing them to intermittently flash like distant beacons. In 1912, astronomer Henrietta Swan-Leavitt discovered that the brighter a Cepheid was, the slower it would pulse, allowing astronomers to measure a star's absolute brightness and thus its distance. It was a groundbreaking discovery that turned Cepheids into valuable standard candles to measure the universe's vast scale. By combining observations of Cepheids, cosmologists can build cosmic distance ladders, each rung taking them a step further back in time. It's one of the most precise methods that cosmologists have today for measuring distances. To build a distance ladder, astronomers start by picking nearby Cepheids and cross-checking their distances based on their pulsating light with those found by trigonometry. Wendy Friedman, an astrophysicist at the University of Chicago, said the next rungs are added using Cepheid readings alone. Astronomers then look at the distances of the stars and supernovae on each rung and compare how much their light has been redshifted, stretched to longer, redder frequencies, as the universe expands. This provides an accurate measurement of the Hubble constant. In 2019, the method was used by Rees and his colleagues, who pointed the Hubble Space Telescope at one of the Milky Way's nearest neighbors, the Large Magellanic Cloud. Their result was striking: an incomprehensibly high expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurement. However, Hubble lacked the crucial accuracy for the dense regions of space the team was studying, causing some distant Cepheids to blend into neighboring stars. Despite this, cosmologists had some room to argue that the result, though stunning, might have come from a measurement error. When James Webb launched in December 2021, it was poised to either resolve the error or confirm it. At 6.5 meters wide, Webb's mirror is right 3 times the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 3 times fainter than Hubble can, but it is also much more sensitive in the infrared range, enabling it to see a broader spectrum of frequencies. By examining Cepheids measured by James Webb in the galaxy NGC 4258 alongside Type Ia supernovae, another standard light since they all explode at the same absolute brightness, in distant galaxies, Rees and his collaborators arrived at an almost identical result: 73 kilometers per second per megaparsec. Other measurements, including one by Friedman with the Hubble Space Telescope on the fast-changing light of the most luminous tip of the red giant stars and another with light bent by the gravity of massive galaxies, returned individual results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using gravitational lensing also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Rongan Kai, a cosmologist at the University of California, Merced, who has been working to resolve the Hubble tension, the CMB temperature is measured to 1% accuracy, and the Cepheid distance ladder measurement is approaching 1%. So a difference of 7 kilometers per second, though it is not large, is highly unlikely to be a random chance. There is clearly something to resolve. The new result leaves the answer wide open, dividing cosmology into factions pursuing vastly different explanations. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 meeting at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who found evidence for dark matter, said at the time, "No one wanted to give up their toy." Each person involved was so firmly invested in their own results and so sure that their observations and their measurements were done correctly that it left people only wanting to figure out how to explain it. In February 2023, with James Webb and another independent Hubble Distance Ladder result confirming the Hubble tension, cosmologists are left with three potential explanations: measurement errors, new physics, or some combination of the two. Kai explained that most of the data supports new physics. The simplest and most popular theory is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe look smaller when we look back to the early universe, making the expansion rate appear faster today. There are other explanations, such as the possibility that there are two types of dark energy or that dark matter interacts with light. But these explanations present complexities that cosmologists are wary of. Without further information, dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's advanced new imaging technology enabled it to see galaxies formed only 300 million years after the Big Bang. However, while examining the universe's beginnings, cosmologists saw that these early-stage galaxies are far more massive and advanced than the standard model predicts. Early galaxies should have been full of young, hot stars forming at breakneck speed, but James Webb showed that many of them were overflowing with heavy elements from earlier generations of stars and actively developing massive black holes at their centers. James Webb's observations have intensified the debate in cosmology by providing precise data that confirms existing discrepancies and reveals unexpected insights about early galaxies. Resolving the Hubble tension and understanding these early galaxies could require new physics or a major revision of the standard cosmological model. The search for these answers is likely to be one of the most exciting frontiers in modern astronomy. James Webb Space Telescope, JWST, has not only transformed our understanding of early galaxies, but has also opened new avenues for exploring fundamental questions in cosmology. Its infrared capabilities allow it to peer deeper into the universe than ever before, capturing light from some of the earliest galaxies formed only 300 million years after the Big Bang. These observations have challenged the prevailing theories of galaxy formation, suggesting that early galaxies were not primitive, youthful structures but were surprisingly advanced, containing heavy elements and hosting supermassive black holes at their centers. This discrepancy between theory and observation raises critical questions about the processes driving galaxy evolution in the early universe, hinting at potentially more rapid and efficient mechanisms than previously thought. Moreover, JWST's discoveries have exacerbated the long-standing mystery surrounding dark matter and dark energy. These elusive components, which make up most of the universe's content, remain poorly understood. Dark matter, which interacts gravitationally but not electromagnetically, plays a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts, its exact nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. Dark energy, responsible for the accelerated expansion of the universe, presents an even more puzzling challenge. The standard cosmological model treats dark energy as a constant, uniform throughout spacetime, but anomalies like the Hubble tension suggest that its properties may not be so uniform. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially affecting the universe's expansion rate differently in various epochs. Resolving these mysteries requires not only advanced observational capabilities like those of JWST but also theoretical frameworks that can accommodate new data without